Newton's first law of motion states that an object at rest will stay at rest unless acted upon by an outside force. This is applicable to swimmers jumping off of a block or pushing off of the pool wall to start swimming. For example, when a swimmer is waiting on the diving block for the official to blow the whistle for them to jump into the water, they are at rest. Then, once they push off of the block exerts an equal and opposite force against their feet, which launches them into the water for them to start swimming. Newton's second law of motion basically gives us the equation that force equals mass times acceleration. This can be used to explain why some people swim faster than others. Here is a video of a swimmer doing the butterfly stroke. As you can see, when they push their arms down, it propels the water backwards, and the water exerts an equal and opposite force against the arms of the swimmer to propel them forwards. If we had two swimmers of the same mass doing this stroke, it would simply depend on who is pushing the most when they push down with that motion that they're making with their arms and their legs, because in F equals ma, for there to be a greater acceleration, there needs to be a greater force. And since both swimmers are of the same mass, then mass does not play a part in determining who would be faster. As another example, I exert more force in the first clip and go faster. As I've stated a few other times in this video, for every action there is an equal and opposite reaction. This is Newton's third law of motion. Let's apply this to swimming. Swimmers have to stroke down and backwards against the water to stay at the surface and continue thrusting forward. The movement of a swimmer's arms opposes the force of the water going against them. We can also apply this to when a swimmer is dolphin kicking. The water pushes back on the swimmer, which propels them forward. Dolphin kicking, however, results in more thrust than normal flutter kicking. So, in the video behind me, you can see that a swimmer is starting off swimming with dolphin kicks. Swimmers do this to start off swimming because it propels them more, because it's a bigger motion than just flutter kicking and moving your arms. The bigger the motion that you make with your legs, then the more force that the water will push back on you to propel you forward. The smaller your dolphin kicks are, then the less force that you will be propelled with. Our next physics concept is buoyancy. To swim, buoyancy is needed to lift a person so that they stay at the surface of the water, so when their arms come up, they only have to deal with air resistance, not water resistance. This concept is basically explained by Archimedes' principle, which states that any object suspended in a fluid has an upward buoyant force acting on its center of buoyancy that is equal to the weight of the displaced fluid by the object. Buoyancy plays a part in rotational and translational equilibrium. For a swimmer to be at rotational equilibrium, the buoyant force needs to be acting through the center of buoyancy, not through the center of mass. For translational equilibrium, the upward buoyant force needs to be equal to the weight of the object. The equation for buoyancy can be described as the negative fluid density times the acceleration due to gravity times the fluid volume. Buoyancy is obviously important when we're talking about swimming because it is needed to keep the swimmer afloat and not drowning. Swimming is very different from sports like track and tennis. It involves water resistance instead of air resistance, which means that swimmers face stronger drag than track runners. This drag force results from skin friction with the water, a swimmer pushing down on the water, and the waves produced by the swimmer that come back in contact with the swimmer. The drag force is present whenever an object is moving through a fluid. And from the equation that you can see on the bottom left of the slide, the faster that an object is moving, the more drag there will be, because you multiply the right side by velocity and drag is on the left. So the greater velocity, then the greater drag you will have. From this equation, you can also see that the greater the cross-section area between you and the water, then the greater the drag force will be. So keeping your form as straight and as horizontal as possible will eliminate drag. In turn, decreasing drag will make you swim faster. Sometimes for the swim team, we have practices called drag practice, where we wear normal clothes so that it requires more effort for us to swim, making it more of a workout. Raelee, I see a lot of issues with drag going on. To fix this, you should swim in a more horizontal position, which means keeping your head down and your body aligned with your head so that you're more like this instead of like this, creating less surface area with the water, which means less drag. I would also recommend keeping your elbows close to the surface of the water, staying in a tight streamline when you start swimming and after your flip turns, keeping tighter kicks and pointing your toes, as well as, if you choose to do so, shaving your body hair and wearing friction-reducing swimsuits. Raelee, you need to stop skipping leg days so that you can produce a stronger force against the diving block, therefore causing an equal and opposite reaction that will propel you more. Raelee, I changed my mind. You also need to work out your arms more so that you can push against the water, therefore making the force that it exerts back onto you greater.